You are listening to EETimes On Air, and this is EETimes Current. I'm Eric Singer. Today's podcast is sponsored by Synopsys. Our technology, your innovation. Our guest today, Hezi Saar, is Executive Director of Product Marketing at Synopsys, where he leads the mobile, automotive, and consumer IP product lines. He brings more than 20 years of experience in the semiconductor and embedded systems industries. Hezi holds a BS in computer science and economics from Tel Aviv University and an MBA from Columbia Southern University, as well as executive certificates in strategy, innovation, management, and leadership from the MIT Sloan School. He also serves as chair of the MIPI Alliance Board of Directors, which defines interface specifications for the mobile, automotive, IoT, physical AI, and related industries. Hezi, thank you so much for joining us on the show once again.
Awesome. Thank you for having me again.
Hezi, let's start by having you break down what's new in AI. And if you can, let's talk a little about why physical AI has suddenly become the headline.
Yeah, AI is everywhere. Is it new? No, not that new. But I guess what we have seen is really an explosion in electronics in the semiconductor market as relate to AI. The market is growing very rapidly. There was a projection that the semiconductor market will reach $1 trillion by 2030, but the recent updates are seeing that even this year, 2026, we're going to be more than $1.3 trillion. So the AI-driven industry growth is really driving semiconductor growth. AI workloads are driving, say, historic growth in the semiconductor revenue. So definitely AI-related silicon is really dominant and will account for growing a portion of the total semiconductor revenue, powering GPU, CPUs, accelerators, as we see that. Part of the growth in semiconductors is the memory price inflation that we see and the demand for it. But a big portion of it is really data center expansion. AI data center expansion really driving CSP, CapEx year over year, like about 80% growth, which is huge. But if we're talking about AI or what's new in AI, it's really more beyond the data center. So there's an expansion that goes beyond the cloud data centers into edge AI and physical AI domains. So these are the robotics and autonomous machines that we have. So beyond the cloud AI semiconductor growth that we have discussed, so that for the components we said CPU, GPU, accelerator, etc. There's an edge AI expansion, or like embedding AI compute in many devices, physical AI market growth that is really going after the autonomous machines in general, autonomous systems, robotics, and all three of those AI, cloud AI, edge AI, and physical AI really provide a demand for advanced semiconductor in our industry. I think coupled on top of those three markets is the system level semiconductor value that is being brought, because the semiconductor itself right now, it's really becoming a system. So looking into coupling memories, coupling accelerator, packaging technologies, interconnects, and power delivery as well, all of them are critical alongside the compute in AI hardware.
So you mentioned robotics and autonomous systems, which I think are the first things that most people think of when we talk about physical AI. But tell us, how do you define physical AI, and what forces are pushing the industry away from cloud-only designs?
Yeah, so physical AI, for the way we see it, is autonomous systems. I think it's part of the definitions that we see in the market. So those autonomous systems look like robots, self-driving cars, but any autonomous system that has the capability to perceive, understand, reason, and perform complex action in the physical world. So this typically have multimodal AI enabling those autonomous machines. I'm generalizing it, that have these three components: perception, so perceive the world through their senses. You can say computer vision, but it can be any sensor or sensors. The second one is understand the instructions. So that can come from the operator, the human being. It could be through natural language, could be whatever means. And the third one is to translate those perception and understanding of the commands to physical actions. So when we look at the differences between, let's say, physical edge AI to the cloud AI, there are distinct differences. And when the user or the consumer is really using the AI capability on device itself, typically provides multiple benefits such as privacy. So we don't want to have your private information be around in the cloud somewhere. You want it to be local. Data security, that you want that to be protected. It could be any security. It could be any data that related to your work or your personal data. The fact that you have an AI on device itself, and it could be physical or edge, it doesn't matter too much, means that this AI capability can be personalized, can be relate to you and your taste and preferences going forward. AI on device would improve responsiveness for several tasks that can be utilized on device, and in general, less reliance on the cloud that is has some either latency or cost associated with that would provide that kind of benefit. But I want to mention that it's really a fabric. When systems are being created, it needs to be taking into account the the AI inference economics, if we can call it this way, which means that latency, bandwidth, recurring costs, all of these are really the dominant constraints. It's not really training. So we're talking about more inference, either on the cloud or on device itself. So CSPs will continue to accelerate their CapEx investments going forward. It will not stop. The only thing is that for that investment, so inferences that's being done on the cloud, now there'll be edge or on device or physical AI on device inference that offloads the majority of what we can call the predictable high frequency queries that maybe today are going to the cloud, but if used wisely, it can be utilized and be provided or exercised on device itself. So not to mix things. So cloud AI retains to be the frontier, reasoning, multimodal fusion, orchestration, and continuous learning. But offloading it to the edge or to physical AI device will result with a hybrid inference architecture that would improve the ROI and better consumer experience going forward. So we're looking at it this way, then the edge AI, physical AI are really complementary to the cloud AI. They're not substitution for it. And hybrid inference seems to be the default architecture when designing high impact device at the edge going forward. Of course, there'll be those devices that could be solely using processing on device itself. It depends on the complexity of the device, but hybrid inference seems to be the one that will be probably dominant going forward.
Sure. And you've given us some great examples in terms of latency and the other reasons why it's really not a one size fits all solution when it comes to cloud or the edge or on device. Hezi, one of the reasons that we love having you on the show is that you bring the engineering side as well as the economic side. So let's switch to that side of your brain now. And I want to ask you about where you see the market opportunity here and why should semiconductor leaders care about this?
Wow. Yeah, well, thank you. It's a great question. I think what we look at is that, right, we're looking to create value, and value would create expansion in the market. So physical AI, as the topic of our discussion here, is expanding the silicon content per machine. So it's not just the unit volume. Unit volume, well, it will rise for sure, but it's really the content, the semiconductor content per device. If we look at, say, probably one of the most complex physical AI um, example that is used today is the humanoid. Really, it's a powerful, you could say, proxy for the broader physical AI wave that we're discussing right now. It
Yeah.
has the full stack of sensing, processing, the memory storage, connectivity, power, and as well as safety control. So each semiconductor, so the semiconductor content for each humanoid is between $1,000 to $2,000 US right now. This is similar to what we would expect to have in terms of semiconductor content in a car.
Yeah.
It's orders of magnitude from higher than any other consumer electronics, typical consumer electronics. So this is really provides a huge opportunity for semiconductor industry or players to participate. And with looked at some numbers like $10 billion market by 2035 and over 50 billion by 2045. It's mind-boggling. So if we can just service that with the right electronics, of course, it will be beneficial for everybody. And at this point of time is the opportunity that we're seeing now. I want to mention that humanoids are used here as an illustration of the market, but physical AI is not just humanoid,
Right.
but it's really an example why physical AI is taking off. It's taking off because without changing the infrastructure that we have around us, right? We're humans. We use doors, chairs, windows, shelves, tools, whatever we use,
Hmm.
could be used also with the robotics that could be complementary for us. And so deploying them in their existing world, and rather than really rebuilding the world for them, is really what would make a difference. So the AI innovation here is expected to be utilizing this kind of benefit. So, but with the first use case, of course, being the technology where it's going to be more mature and can be really utilized at the beginning, like such as manufacturing, logistics, and retail.
Right. So we've all been chatting with LLMs for years. More recently, we've watched LLMs chat with each other. What changes when you give a machine eyes, hands, and mobility? And how did models evolve towards vision language action, what we call VLA?
Yeah, it's first I would like to say that the models are still evolving, but from the chatbot kind of capabilities, so LLM could really provide a text output to a text input. So when you ask a question, it can predict what the answer would be and provide that. And in the second category, we'll be adding more vision into the model. So we
Mhm.
have VLMs, different kinds of VLMs that would actually get both text and visual data as input, and then would interpret, describe, analyze the image or the video and the text all together, and would provide a response to that. The VLA is really adding the action component. So now you have a vision, language, and action all together. So to let's say a robot, a humanoid, where it gets a command, put the ball in the box or do something, they need to scan the environment and find the box, find the ball, understand reason. So they have the command is coming in, and then you have the visual, and then it needs to be interpreted to an action by moving the robot towards the ball, grabbing it, and putting it in that box. Now, I think what is still, that's why I mentioned at the beginning, VLA is not an end of a game for
Right.
physical AI. It is because the physical AI and the robotics itself, they are still being defined and developed. So we see a move to a world model driven AI. So more prediction and simulation and planning in the physical space. So instead of really having everything canned, what this world model would do would enable the physical AI device to move to I imagine, I decide, I act. So instead of really acting upon that, but instead of that, looking at the world, building an eternal world state, simulate before act, and then plan the sequence of events of what would happen, and then only then execute, and then continuously learn. So update the state, the world state based on what happened, resimulate for each step. That will provide us some more intelligent systems that are not just getting commands, but actually really understand the surrounding.
Next, I'd love for you to break down the physical AI application spectrum more broadly. And for our listeners, most of whom are designers, can you talk a little about the design constraints that they need to take into consideration?
Sure. Let's discuss the variety of, let's say, physical AI electronics, and we can look at it based on performance. This is typically how things are looked at. However, there is a shift towards looking at not just performance like computer performance, such as TOPS, but TOPS per watt. Because what can you get me in this performance for the power that I need to pay? Some can just look at it as how many tokens can I generate per watt. So
Hmm.
the metric itself can change based on the application that we're looking for, and but let's try to break it down by performance. So when we look at a simple robotic arm to a vacuum cleaner to a medical device, an AMR, a drone, a humanoid, or a car. This is really what we would look at in terms of performance or tops that we would like to have. And typically, as performance grows, then also the sensing capability grows with it. So computer vision and sensor fusion in terms of how many frames per second or how many inferences per second would grow with the performance and the complexity of the systems. And then what needs to be taken into account, because this is an AI based machine, it needs to be able to respond to the query as soon as it's needed. So the lower end systems doesn't have the same urgency to respond, so to provide the first token, while those that are more safety critical, such as car or even humanoids or drones, will need to have this more optimized. Then there's another aspect of how many tokens you generate per second. So once you really the AI machine is working, then what is the bandwidth that is really needed or can be provided? Because then decision needs to be made real time with the information that is being provided. So latency and bandwidth become really critical how to service those applications. I think right now what we're seeing is that say if we can generalize physical and edge AI together, the latency sensitivity is there, bandwidth is limited, and data privacy regulations all drive the adoption globally. The real time computer vision and multimodal sensing increase really this SoC complexity and the compute density requirements. So we are seeing power, thermal, always on constraints being more emphasized. So AI workloads, they must deliver an acceptable tops per watts. So not just the peak tops as we discussed. So taking into account all the inference lifetime energy consumption is important when we go and design an SoC. Memory capacity and bandwidth bottlenecks are critical. Data movement, stressing the on-device RAM capacity, off-device RAM capacity, memory bandwidth. All of that needs to be taken into account, and also the data and the sensor data explosion. So how do you get the sensor information in the speed that you need? How do you have a multi-sensor fusion creating the information that is needed? So all the ability to provide the sensing information and avoid system bottlenecks. So latency, we mentioned that already. So all the use cases for vision, autonomy, robotics, all of them require predictable bounded latency. So if a cloud is in the loop, meaning you need to rely on inference on the cloud, and the round trip needs to be accounted for and acceptable for the user. And we didn't forget security, privacy, safety. That we have that. And I think right now the challenges on the design is not only what we mentioned, but now we have even the system level complexity and integration. As the market moves so rapidly, then the systems need to span compute, memory, storage, sensors, connectivity, software. All of these needs to be optimized for a hardware software co-design to ensure that the targets, the designs are met, such as PPA and, of course, time to market.
So you've talked a bit about things like latency and security, privacy that are related to the customer experience. Can you walk us through some of the other KPIs and how they relate to the customer experience?
Yeah, we will not be able to touch on all, but I'll try to give some examples. So, really, AI workload for the device defines the choice of design and the rate, bandwidth, efficiency. So, when we talk about efficiency, the AI use case on device are really bounded by the application itself, the power limits, the space, the footprint of the device itself, the heat. So there are constraints in the physical world that needs to be bounded, and that provides really what you can do and what you cannot do. So if you look at the memory, I'll call it subsystem. So the model that is running in it to fit in the working memory, that puts some limitations on not only cost but actually the bandwidth and how you want to utilize it. The output of the model, so the tokens per second, depend on how quickly the model waits and the KV caches are moved. When you look at the storage, it's typically on the storage is really where the model resides. So higher performing embedded storage is required to store that model or models. Reading, so the bandwidth read is critical for user experience because you need to load that into the working memory. Sensors, because we're talking about physical world, so multiple sensors and sensor fusion needs to be accommodated and provided with the right latency, provide high throughput raw data to the SoC. So is that machine vision, machine learning, inference, all of these needs to be combined with multiple sensor connectivities that come in different times and different sources and need to make sense out of it. Security, privacy, safety, so all the encryption that needs to be built in the connectivity, different kind of regulation, cybersecurity, AECQ. All of this needs to be taken into account to ensure that there's no liability from the device itself. And if it is connecting, that device connects to a network, then yeah, you need to ensure that you're doing, and that network is doing a hybrid operation with the cloud, you need to ensure the data movement is done efficiently so the user experience doesn't degrade.
Right. Something we've talked about on this program and we hear a lot these days is about the idea of memory wall. Can you give us an example from your world and talk about how the memory wall issue is addressed in edge or physical AI?
Yeah, so in general, the memory wall really, this is the bottleneck where the AI compute units can operate faster than the data can be delivered from the memory. So this is really not optimizing the system performance or latency or inefficiency. So there are a couple of examples like that. I'll try to provide that in, I guess, in a simplistic way. If you look at the memory in the on-device electronics, it can be whatever. It can be even a phone, but it can be even a robot, whatever. So traditional architecture really consumes significant power. And are not that efficient because there's data movement. You have the SoC, and then you have the model that is stored in the storage device list, for example, JEDEC UFS. And you need to move upon power up. You need to read the model and store it from the storage to the SoC and then to the DRAM that is connected through a DDR, LPDDR kind of an interface. So the bandwidth that provides from the storage to the SoC and then from SoC back and forth to the working memory is really slows down or could potentially slow down AI computation, and that could impact latency, can impact responsiveness of the application. So ensuring that the industry is going after the most optimized, faster in terms of response time and in terms of bandwidth, to provide a quick boot, optimized time for first token to that is critical for the success of this kind of memory wall problem that we're discussing. So when you have high speed storage, in the case of devices are at the edge, is more JEDEC UFS that acts as an active AI data path component, so enabling faster access to the model parameters and the data. Selective buffering into the DRAM, so only relevant model subsets can be buffered or should be buffered to the DRAM during inference. So we can reduce the power and the cost of such an implementation, and then using RAG to dynamically retrieve the external data to augment AI inference. So leveraging something like KV searches in the flash storage would provide efficiencies there. So integrating all of that in an edge AI SoC would really provide an efficient data orchestration. So solve that data movement that we have. So if we put it in practice, so it doesn't sound too techy. If, for example, the user, let's say you have a robot assistant next to you, and the robot assistant was with you in a certain meeting, and you say, ask that robot, okay, what did John promise in the last meeting that we had last week? Then the system itself can retrieve the meeting transcript. The NPU can process the transcript itself. The KV cache stores the attention for that transcript, and then the model will generate an answer using the KV reuse. So that will provide the first response, but then likely, because knowing you as the user, you will have follow up. Okay, now I know what John promised. Okay, what should I do next? You can have follow up questions, and those follow up questions would allow the system to be utilized in a better way. Reuse the KV cache, much faster response, and no need to reprocess the transcript.
That's a great real world example there. Staying with the SoC topic, what does a physical AI SoC need when we compare it to traditional embedded SoCs?
Yeah. So first, I would say physical AI in general is evolving. We are seeing early designs right now that mimic a fusion of mobile compute SoC and mission critical computing, and you can say it's automotive like, but it's a combination. It's a hybrid between the two. First of all, the fact that the SoC needs to have an autonomous cognition and decision making, either by hybrid cloud and local AI platform, multimodal foundation model. So this is really something that determines the memory subsystem we have discussed. So we need to have high speed storage and high speed DRAM access. Of course, the edge AI compute with functional safety and reliability. So this is for all the robotics applications that are evolving. But then the device itself need to have comprehensive interfaces for high bandwidth environment. So sensor fusion is critical for this kind of a physical system, peripheral integration, network communication, if it has a communication to the external world, either wireless or to the cloud, and ability to have a strong enough processor that would allow to have we could say extendable software stack, because software will need to be built and need to accommodate the evolving use cases, because what the hardware is being designed right now, it needs to be flexible enough to have the software to run and enable application that we haven't envisioned yet.
So you are quite active as a leader in the community that that defines standards in the industry. Let's talk some more about how open standards like UFS, PCIe, die to die, how do those standards reduce risk and speed time to market?
Yeah, I think so. This is a duty that companies in the world have, not only to take care of their business, but actually to allow the scalability of the industry to be more viable. So we are seeing different kinds of AI acceleration tactics, you call it, and that could be AI companionships that actually latch to existing SoCs. I just give an example. Since MIPI camera or MIPI receiver, MIPI transmitter kind of ports are available on many SoCs at the edge, AI companionship could latch to those ports and have all the secret sauce on the imagery done there. So we are seeing things like that happening. Is it the most common one? Not necessarily, but it's a creative way of utilizing available ports and resources on SoC to innovate.
Absolutely.
We are seeing industry moving towards marrying security and sensing together. So, for example, this is a problem that came, I guess, from the automotive industry, but it can be utilized for any physical AI component, is that you have more and more sensors being used, more cameras. Some of the cars being utilized today are only images. I mean, camera sensors and not necessarily radars or lidars. Some of them are using all kinds of sensors, but cameras for sure are the very dominant in this space, and they need to secure mission critical physical function. We need to mitigate cybersecurity risks, end-to-end protection, component authentication. So you need to have standard approach with high level of flexibility to enable ecosystem health and adoption. So having MIPI Alliance come up with CSE 2.0, which is a solution that provides that layer of camera security, is helping to solve that problem, not just in automotive initially, but actually in any edge or any physical AI going forward. You discussed a multi-die, and the multi-die I would think it's in infancy at the moment in the edge. It is happening, of course, in high-performing SoC, but it's still not got into the full potential. I think as market continue to evolve with higher compute requirements and higher complexity and lower cost on the multi-die technology, they need to have memory closely coupled with the SoC. We talk about the memory wall. So optimizing the memory integration will allow a tightly coupled AI acceleration with that memory, potentially enabling workloads we haven't seen before. If we're talking about humanoids that are right now at 50K, but maybe they need to go down to something that's just cheaper, so will be more affordable for the user, it could be that this kind of capabilities with cost reduction of reuse of silicon for chiplets used across multiple application and different process nodes would enable this kind of lower cost, smaller footprint, and power saving. So this kind of scalability, either homogeneous computing, so same SoC used on both sides of the die to provide additional compute power, or heterogeneous, which is these are realities right now in the automotive space, and could trickle or would trickle to the physical AI at the high end initially, but then to mainstream going forward. I want to mention that as this physical AI market is in its evolution stage at the moment, with designs that are going in, but higher designs coming into the market, we as an industry also need to ensure that regulatory cybersecurity or security in general is being accommodated. So there are cybersecurity regulations. I just mentioned one, Resilience Act. So it's the EU's plan to make sure all digital products are safe from cyber threats. Is just one thing that needs to, we as an industry and electronics and semiconductor needs to pay attention to, and ensure that we're not only providing the functionality, but providing the system that would actually be safe and secure to be used by humans.
All right. So, final question. What's the call to action for the whole ecosystem in the next 12 to 24 months from your perspective?
Yeah, so I may need to change my answer in a couple of months, but it's what I'm thinking right now. First, converging on reference workloads. I think workloads and architecture, our architectures are being defined right now. There are market makers that are working on it now, including Synopsys with our partners. But those architecture and workloads need to reflect reality. The reality would be those where we can, provide value initially. I mentioned the more industrial automation kind of use case that is driving the initial adoption, but it will not stop there. So ensuring that we as an industry have workloads that we are optimizing for are mission critical, safe and secured. That will be one, because driving the beachhead first with the leading application would enable us to improve and optimize the architectures going forward. Secondly, we already know system bottlenecks. We already know where they are. So we mentioned the memory bandwidth, storage, sensor ingress, and interconnect overall. As data movement dominates the power and latency, and we know this is 100% related to user and satisfaction, and the fact that we would use it more or less. This is something we as an industry need to continue to work on optimizing and reducing the bottlenecks there. And third, I think standardization won't hurt. So finding standards that we can all align, having common language, you can say, between semiconductors, IP vendors, and electronics that know how to develop what will be the upgrade path. Maybe using humanoids as a mission critical system where we drive functional safety, cybersecurity, commonality, and then borrowing that solution we already solved, like in the automotive space or industrial space, and borrow it to the physical AI space to make it more viable and more available. So then we will be able to provide an ecosystem that will be robotics specific standard, but will be also mature and will rely on problems that we already solved. And I think the last one is just because I have the MIP Alliance chair hat as well. MIP Alliance right now, I've started with the MIP Physical AI, Birds of a Feather. This is an example that how the industry wishes to come together and align on connectivity standardization. So this is really where a place where OEMs, tier ones, semiconductor players, or all semiconductor industry can come together and discuss where we can improve, what we can use as the baseline, what is missing, and if there is a missing issue or it is a problem that needs to be solved, this is one place that can happen. I'm not saying it can happen somewhere else, but we need to talk. We need to solve the issues as they come along and to solve all the issues and the growth and define a path for the industry going forward.
Well, I'm so grateful for you, not just for coming back on the show today, but also for the work that you and Synopsys are doing to enact those standards and just your leadership in the industry. Hezi, thank you so much for being on the show again and for all you're doing.
Thank you very much. I enjoyed it as well.
That brings another episode of EETimes Current to its end. Thank you for listening, and thanks again for Synopsys for underwriting this episode. EETimes Current is available through the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript along with direct links to the other stories we've mentioned and other resources. EETimes Current is produced by EETimes and Coop Studios. Our editors were Helena Melberg and Aaron Garrison. I'm Eric Singer. Thanks for listening.